In this lesson, we're going to be deriving the derivatives of the inverse trigonometric functions. So here we're going to find the derivative of the inverse sine of theta. And we'll start by writing inverse sine of x. Y is equal to the sine of x. This is our starting point, inverse sine of x. And we're looking for what is y prime. That's what we're trying to find. So move this up. Okay, so what we want to do is we want to start by taking the sine of the left and the right-hand side of this equation, keeping it balanced, right? So I'm going to take the sine of the left-hand side, which is the sine of y, and then I'm going to take the sine of the right-hand side, which is the sine of the inverse sine of x. And this keeps my equation balanced. I'm doing the same thing to both sides. Okay, so what you can see here is that I've taken a composite of two functions that are inverse of each other, and the sine of the inverse sine gives us back the input, which is x. So what I get is that the left-hand side, which is the sine of y, is equal, what? Yeah, I'm not recording?
You weren't.
Okay, so we'll look at the first trigonometric identity, which is that the sine squared x plus the cosine squared x is equal to 1. I suppose in this case we should not be using x. Let's use y, just so that we're matching. And that's 1. There we go. My mistake. Okay. So the sine squared y plus the cosine squared y is equal to 1. That's our first trigonometric identity. And so what we want to do is we want to solve for the cosine of y using the first trig identity. Well, if we subtract the sine squared y from both sides, we get the cosine squared y is equal to 1 minus the sine squared y. And if we take the square root of both sides, I take the square root of the left, and I take the square root of the right, I get the absolute value of the cosine, the absolute value of the square root of the perfect square is the absolute value. So that's going to be the absolute value, the absolute value of the cosine of y, that's what that gives us, is equal to the square root of 1 minus the sine squared y, which means that the cosine of y would be plus or minus that value. But in this particular case, it's all positive because our arcsine has domain restrictions. So we end up with y prime is equal to 1 over the cosine of y, which is 1 over the square root of 1 minus the sine squared y. And what we see here is that this sine squared y, well, at least the sine y part, the sine of y is equal to x. So we can just substitute in x for the sine of y, and we get y prime is equal to 1 over the square root of 1 minus x squared. And I need you to commit that to memory, but that is the derivative of the inverse sine of x. So let's write that in up here. So y prime, if y is equal to the inverse sine of x, is equal to 1 over the square root of 1 minus x squared. So now we're going to find the derivative of the inverse cosine of x. And so you go to black, and we're going to start by writing out that y is equal to the inverse cosine of x. I'll move that up. And so what we're going to do here is, keeping our equation balanced, we're going to take the cosine of both sides. So we have the cosine of y is equal to the cosine, this is the right-hand side, of the inverse cosine of x. We'll move that up. And what we can see here is that we are taking the cosine of the inverse cosine, which is a composite of two inverse functions, and that gives us back our input. So the left-hand side is the cosine of y. And the right-hand, what's the right-hand side equal to? X. Right. X. Let's write that down. Okay, so now we're going to use implicit differentiation. We're going to take the derivative from the left to the right with respect to x. So we're going to take the derivative with respect to x of the left-hand side, which is the cosine of y, and of course y is a function of x. And on the right-hand side, we're going to take the derivative with respect to x of x. Okay, so the left-hand side, we're going to do the chain rule and take the derivative of the cosine of y with respect to y times the derivative of y with respect to x. What is the derivative of the cosine of y with respect to y? Negative sine y. So it's negative sine of y. And the derivative of y with respect to x is y prime. And the derivative, oh, I forgot to put the x here. The derivative of x with respect to x is 1. So now remember, we're solving for y prime. In fact, I can put that up here. We're looking for what is y prime. And so we are going to divide both sides by the negative sine of y. And we get y prime is equal to 1 over, and I'll put the negative sign up here, the sine, negative 1 over the sine of y. So now we're going to use our trigonometric identity, which is that the sine squared y plus the cosine squared y is 1. And what we're going to do is we want to solve for the sine of y, right, in terms of the cosine of y, because we know the relationship between the cosine of y and x, and we do not want y prime in terms of y, we want it in terms of x. So if I solve for the sine of y, I will get the sine of y is equal to plus or minus the square root of 1 minus the cosine squared y. And in this particular case, it's going to be positive, okay? That the sine of y right here is going to be actually positive because of our domain restriction. And we end up with y prime is equal to a negative 1 over the square root of 1 minus the cosine squared y. And we know that the cosine of y is x, therefore this is equal to a negative 1. We're going to substitute in an x for the cosine of y, and we get the square root of 1 minus x squared, and there we have it. The derivative of the inverse cosine of x is a negative 1 over the square root of 1 minus x squared. So here we're going to find the derivative of the inverse tangent of x. So let's start with writing y is equal to the inverse tangent of x, and we're looking for y prime, which is the derivative of the inverse tangent of x. So let's start with this first equation, and we're going to take the tangent of both the left and the right-hand side. And when we do that, we're going to have the tangent of y, that's the tangent of my left-hand side, is equal to the tangent of the right-hand side, which is the tangent of the inverse tangent of x. And what we see here is that we are taking the tangent of the arctangent, which is the composite of two inverse functions. So it's going to give us back our input. So we end up with the tangent of y is equal to x. And you can see this is kind of a common theme how we do this, right? Now we're going to use implicit differentiation, and we're going to take the derivative with respect to x of the left-hand side, which is the tangent of y, remembering that y is a function of x, and then the derivative of the right with respect to x, which is the derivative with respect to x of x. Now the left-hand derivative is, we need the chain rule. So we're going to take the derivative of the tangent with respect to y times the derivative of y with respect to x. What is the derivative of the tangent with respect to y? Secant squared, that's right. So this is the secant squared of y times the derivative of y with respect to x, which is y prime, is equal to, and the derivative of x with respect to x is 1. Keep in mind that we're looking for y prime. So we want to divide both sides by secant squared y. Y prime then is equal to 1 over the secant squared y. So we've just found y prime in terms of y, but we want y prime in terms of x. And we don't know what the secant of y is in terms of x right now, but we know what the tangent of y is in terms of x. So we're going to go back to our trigonometric identity. The sine squared of y plus the cosine squared y is equal to 1. This is one. Everybody remembers this one. And what we're doing here is we want to find secant squared y in terms of the tangent squared y, or secant y in terms of the tangent. And so I know that if I divide the sine squared y, I'll get the cosine. So let's take this entire equation and divide both the left and the right by the cosine squared y. And so I've divided the left-hand side by cosine squared y and the right-hand side by the cosine squared y. And what do I get? Well, I get the tangent squared y plus 1 is equal to the secant squared y. Well, that's what I have here. I have the secant squared y. So I can just sub that right in. And I can say, back to black, I can say that y prime is equal to 1 over the secant squared y, but I just discovered that the secant squared y is the tangent squared y plus 1. Now, if I look at what the tangent of y is equal to, the tangent of y is equal to x. So I can replace the tangent of y here with x and make this an x squared because it's squared, and I get 1 over x squared plus 1. And here I have the derivative of the inverse tangent of x, which is 1 over x squared plus 1. That's the derivative of the inverse tangent of x. So now we're going to find the derivative of the inverse cotangent of x. So we'll start with writing y is equal to the inverse cotangent of x. And as we've been doing all along, we're going to take the inverse of the inverse cotangent function, which is the cotangent function, and we're going to operate that on both the left and the right. So we're going to take the cotangent of y on the left And on the right-hand side of our equation, keeping it balanced, we're going to take the cotangent of the right-hand side, which is a cotangent of the inverse cotangent of x. And as we've done before, we see here that we are compositing two inverse functions. So what's going to come out of this is our input, which is x. So on the left-hand side, we have the cotangent of y is equal to x. And now we're going to use implicit differentiation on the left and the right and take the derivative with respect to x of the left-hand side, which is the cotangent of y, is equal to the derivative with respect to x of the right-hand side, which is x. Now, on the left-hand side, we're going to use the chain rule, so we're going to take the derivative of the cotangent of y with respect to y times the derivative of y with respect to x. What is the derivative of the cotangent? Yeah, it's negative cosecant squared y. And we chain it out and multiply it by the derivative of y with respect to x, which is the y prime. That's what we're looking for. And the right-hand side is 1. Derivative of x with respect to x is 1. Now, we're looking for y prime. So we're going to solve for y prime by dividing both sides by the negative cosecant squared of y. So y prime is equal to a negative 1 over the cosecant squared of y. So we have just solved for y in terms of y, but we want to solve for y in terms of x. We don't right now know what the cosecant of y is in terms of x, but we know what the cotangent of y is in terms of x. So let's use our first trigonometric identity, which is that the sine squared of y plus the cosine squared of y is equal to 1. And we're looking for the tangent and the cosecant. So let's divide both sides, this time, divide both sides by the sine squared y. And that's going to give us our cotangent and our cosecant. So we end up with 1 plus the cosine of the sine is the cotangent. Cotangent squared y is equal to the cosecant squared y. And there we have it. We've got what the cosecant squared y is equal to. It's equal to 1 plus the cotangent squared y. So this is equal to negative 1 over 1 plus the cotangent squared y. And we know that the cotangent of y is equal to x. So we get y prime is equal to a negative 1 over 1 plus x squared. And we can write this up here. Y prime is equal to a negative 1 over 1 plus x squared when y is equal to the inverse cotangent of x. So now we're going to derive the derivative of the inverse secant of x. So we're going to start with writing y is equal to the inverse secant of x. And what we're looking for is y prime. So what is y prime when our function is the inverse secant of x? And I need a little negative 1 there. There we go. Let's move this up. I want to make sure we have enough room for all this. Okay. So we want to start by taking the secant of the left and the right-hand side. So we're going to keep our equation balanced by doing the same thing to both sides. And that is, we're taking the secant of the left-hand side and the secant of the right-hand side. And on the right-hand side, we're taking the secant of the arcsecant. So what we have here is we are compositing two functions that are inverse of each other, and the result will be the input, which is x. So we end up with the secant of y is equal to x. Now we're going to take the derivative. We're going to use implicit differentiation and take the derivative of the left-hand side with respect to x and the derivative of the right-hand side with respect to x. And the derivative, this is a chain rule here, the derivative of the secant of y with respect to y is secant y tan y times y prime, that's a chain rule, is equal to the derivative of x with respect to x is 1. And now we're going to solve for y prime by dividing both sides by the secant y tan y. So we have the secant of y and the tangent of y. And what we can see right away is that the secant of y is equal to x. So that means that y prime is equal to 1 over x times the tangent of y. Now we have a restriction on x, which is going to make this the absolute value of x, because x, which represents the input to the arc secant, is the trigonometric ratio and of 1 over the cosine, and that is going to be restricted to being positive for the inverse secant. So now we need to find out what the tangent of y is, and what we're going to use, because we're going to look at the fact that we know that the secant of y is equal to x. Given that information, what is the tangent of y? So we're going to go and look at our trigonometric identity, the sine squared y plus the cosine squared y is equal to 1. And we're looking for the tangent. So we know that the sine over the cosine, so we're going to divide this identity on the left and right hand side of this identity by the cosine squared y. And we end up with the tangent squared y plus 1 is equal to the secant squared y. And we're solving for the tangent of y, so the tangent squared y is equal to the secant squared y minus 1. And we're going to take the square root of both sides. And we end up with the absolute value of the tangent of y is equal to the square root of the secant squared y minus 1, which means that the tangent of y is equal to a positive or negative square root of the secant squared y minus 1. And in this particular case, the tangent of y is going to be positive, otherwise we don't have a function, we have a relationship. So it's the square root of, and we know that the secant of y is equal to x, therefore we're going to replace the secant y with an x, and this becomes x squared minus 1. So if we substitute this in, we end up with y prime is equal to 1 over the absolute value of x times the square root of x squared minus 1. So let's put this up here. We have y is equal to the arc secant of x, therefore the derivative y prime of the secant, the inverse secant of x, is 1 over the absolute value of x times the square root of x squared minus 1. So now we're going to derive the derivative of the inverse. And our last derivation here is to find the derivative of the inverse cosecant of x. So we start by saying we have y is equal to the inverse cosecant of x. And we're going to follow what we've been doing all along by taking the cosecant of the left and the right hand side. So the cosecant of y is equal to the cosecant of the inverse cosecant of x. And right here, what we have here is a composite of two inverse functions, which is going to yield the input of x. And that gives us the cosecant of y is equal to x. So now we're ready to take the derivative of the left-hand side and the right-hand side with respect to x. So the derivative of the cosecant of y is equal to the derivative with respect to x of x. And on the left-hand side, we're going to use the chain rule. The derivative of the cosecant of y with respect to x is the derivative of the cosecant of y with respect to y times the derivative of y with respect to x. And the derivative of the cosecant is a negative cosecant y cotangent y times y prime, that's the chain, is equal to the derivative of x with respect to x, which is 1. And now we're going to divide both sides by a negative cosecant y cotangent y, and that's part of solving for y prime. And we get it's a negative 1 over the cosecant of y times the cotangent of y. So this gives us y prime is equal to negative 1 over, and the cosecant of y we found up here is equal to x, and in this case it's the absolute value of x because of a restriction. And now we need to find the cotangent of y in terms of x. Well, for that we're going to use our trigonometric identity, cosine squared y plus the sine squared of y is equal to 1. And since we're looking for the cotangent, which is cosine over sine, we're going to divide both the right and the left-hand side of this equation by sine squared y. And by doing that, our first term on the left is the cotangent squared of y, and that's plus 1, is equal to the cosecant squared y, which means that the cotangent squared y is equal to the cosecant squared y minus 1. We'll take the square root of the left and the square root of the right, and we end up with the absolute value of the cotangent of y is equal to plus or minus the square root of, and in this case, we know that the secant of y is equal to x, so we put an x here. It's x squared, because the cosecant of y is equal to x. This is x squared minus 1. And for the particular cotangent of y that we're looking for, because of our restrictions, this is going to be positive square root of x squared minus 1. And so we can take that, and this value for cotangent of y is replaced with what it's equal to in terms of x, which is the square root of x squared minus 1. So we have that if y is equal to the inverse cosecant of x, then y prime is equal to a negative 1 over the absolute value of x times the square root of x squared minus 1.